Right, so let's see. Find a parametric representation for the surface. This is number 23, 6.623. Find a parametric representation. Okay, for the surface. This is a part of the sphere. The sphere is given by x squared plus y squared plus z squared equals 4. There are lines above the cone. Right. Let's sketch the graph. So this is a sphere. You just need to determine, this is a sphere. The cone, how does a cone look like? The cone looks like that. If one extend. So you are talking about this portion of the sphere, right? By above, above the cone, right? It's not the portion below the cone. The cone has, right? So this is a portion. All you have to do is determine, you're going to use a spheric coordinates to describe the surface. But for an arbitrary point here on the surface, you draw the line, you get the phi, right? And you project it to the xy plane, and you get the theta. This is how do we construct the spherical coordinates for the point. Okay, if this point has coordinate x, y, z, then remember x is going to be, rho is 2 because 4 squared. 4 is 2 squared, so it's 2, right? And this will be sine phi and cosine theta. Y equals 2 sine phi sine theta. Z equals 2 cosine phi. And clearly you can rotate this point around the z-axis. So the theta, no restriction on the theta. Theta is between 0 and 2 pi. But the phi cannot be too large, otherwise it will be below the cone. All you have to do is to determine the largest possible value for the phi, right? Phi is definitely between 0 and somewhere. So look at the two-dimensional picture. Okay, this is y, this is z. Okay, and the cone on this on the yz plane, because x is going to be a 0, so z is just equal to y. Okay, z is going to be actually absolute value y, because when x equals 0, which is the square root of y squared, which is just 1. So there's two sides. So this is the largest possible phi. Phi here is going to be pi over 4, 45 degrees, right? And the cross-section of the sphere with the YZ plane is just as a semicircle. Okay, so imagine, just look at the YZ plane. And the cross-section of the cone with the YZ plane, just 2 lines. So now you can see phi clearly it's between 0 and pi over 2. Pi over 4. So that's it. So this is a parametric representation. If we want to put them in the vector form, this will be like r, phi, and theta, and then you can put x, y, z there. Okay, x, y, z, where x, y, z are given by about the formula. You don't need to repeat it to there, right? So where x, y, z are given by above 3 equations. And then you can use that to maybe find the surface area of that surface. Okay, you have to find the Jacobian, and that's already given. The Jacobian is already given. Okay, and yeah, the Swift. Yeah, you can. Well, you can easily find the Jacobian. Yeah, then you can get the area element. So the next section is section 6.7, is about surface integral. Okay, so you have to use that parameterization. That's the reason before that section we were talking about parameterization for the surface. Then section 6.7, we introduce the surface integral of a function, right? Then right, we recall that, right, for the surface, right, you have a, right, first thing we can do is to, if this is S, right, remember, right, then you can have a function defined on the surface, then you can talk about the surface integral, okay? Now, in order to calculate the surface integral, you have to parameterize the surface. Suppose this is going to be image of some domain D. This is a domain D, okay, covered by the domain D. Then you can pull back the integral on the surface to the integral on this domain. For example, this could be depend UV. Usually use a UV, okay, UV coordinate system, right? And we are familiar with the integral of a domain in two-dimensional in two-dimensional plane, right? So the surface is just a curved plane, right? So it's two-dimensional object. So everything on the surface, okay, can be go back to the plane. So so you can use that to, you can evaluate this using double integral. So here's F, and evaluate at UV, and this part is going to be the cross product and the dA. Okay, so dA is just du dv. Then after that, suppose we have a vector field. This is a function defined on the surface. But if for the same surface, every point you have a normal vector, right? And then suppose you have a bunch of a vector field, right? So the vector field, the inner product is a vector field, and the normal vector is also become a function. So if F is going to be the inner product of the vector field with the normal vector to that particular point, then you get a function. So then you can talk about F dot n ds. Okay. So this is in the book, this part is going to be denoted by this notation. Okay, use a bold letter. Okay, it's ds. Okay, so this is a notation. This is also denoted by f dot d. Yeah, right now I have to put an arrow symbol when you write on it. Actually, they use a, yeah, so this is a notation. Okay, it's harder to draw it, so that's the reason we just simply write ds with an arrow symbol. It's a vector, okay, because it's normal vector times the area element. Okay. Okay, so when you want to evaluate this, we know that the normal, we know how to find the normal vector, right? Since the normal vector, the normal vector is going to be the cross product, then you normalize it. So when you plug into the formula, this can be evaluated. This can be evaluated UV and canceled. So dot product and dA. Okay. So because ds is going to be the norm of the cross product, and the n is going to be the product divided by the norm. So the norm will be canceled out. So this is a formula you're going to use to evaluate the integral of the vector field. Okay, this integral has a name for that. Okay, it is called the flux of F across the surface S. Okay, as some meaning of this. Well, in general, it's very complicated to calculate. Okay, in certain cases, let's do one example. Okay, and then I'm going to talk about the so-called Stokes theorem, which can be used to evaluate this kind of integrals. Okay. So take a look at the example. Yeah, I'm going to take a look at the following example. F is a special vector field defined in the space. Of course, it can be only defined on the sphere. Okay, so this is going to be x, okay, y at the point. Let's say at the point x, y, z. It's going to be x, y, z. Okay, this is actually we call a radial vector. Okay, it's point outside, and it's getting longer and longer when it's getting far away from the origin. Okay, S is the sphere of radius r equals 1, and was a center centered at the origin. Okay. So here's a picture. I just take easy case, okay? So the vector field is going like that. Along the surface, along the sphere, right? So this is F. I think for this particular case, the normal vector, you find evaluate this double integral and ds. Okay, so by definition, this is just equal to the normal vector ds. Okay, now, I can do quickly this in this particular. The normal vector at each point, okay, because it's a sphere, you can skip lots of steps. It's obvious it's point to outside, right? So the normal vector at the point x, y, z is nothing but x, y, z. Okay, it's point to outside. You can find out, but this is even I skip the parameterization. Okay, and since f at the point is also x, y, z, so the dot product of them is going to be the norm. Okay, it's going to be the dot product, which is going to be x squared plus y squared plus z squared. But this is on the sphere, so this is equal to 1 on S on the sphere, because this sphere has a length, it has a radius 1. So when you get a given problem, you have to look at, sometimes you can skip some steps. So this is just the surface integral 1 ds, which is going to be the area of the sphere. The area of the sphere, I know that it's going to be 4 pi r squared, 1 square, which is just 4 pi. Okay. Yeah, I skip keep finding the parameterization for the strip. But if it's because that's so special case, I just chose some idea, and sometimes you can you don't need it to you don't need it to find the parameterization, some special case. Now for vectors, for vector fields, right? There are two parts. Some the general vector field, there are some vectors very special. Right? Some vectors can be viewed as the curl of another vector field. Okay. Okay. So today we're going to talk about the so-called Stokes theorem. Okay. The Stokes theorem says that if S is an oriented piecewise smooth surface that is bounded by a simple closed piecewise boundary curve with a positive orientation. Okay, let me just draw the picture. Okay, so it's a surface, but this is a positive oriented. This is a curve. The boundary. This is a S. S is the boundary of the C is the boundary of the S. Okay, it's oriented in that direction. Okay, so normal vector is pointing this way. Okay, yeah, it's a normal vector. Okay, let's see the picture. So the boundary is a simple closed curve. Piecewise, maybe there are some points, just glue them together. Okay. It's not necessarily smooth everywhere, but it just consists of a smooth curves, several pieces. Okay. Then it says that for an arbitrary vector field, as long as differentiable, okay, then you can this double integral. Okay, it's not a general vector field. Okay, F is a vector field. Okay, so so we only consider special vector field, which is a curl of F, okay, and dot ds. If I evaluate this surface integral of the vector field, okay, over the surface, then this can be, okay, changed to the line integrals. Okay, and here's F and the dr. F, yeah, let's use a dr. Okay. Yes. So if you parameterize a curve, I think before we even mention parameterization, I should say this is a T d little s. Okay? T is a tangent vector. Okay. Once you parameterize a curve, then you can solve the then you can use R to describe this integral. Yeah. So that's it. So that means a surface integral of certain vector field, as long as a vector, it looks like it's very similar to the fundamental theorem of calculus. This involves the derivatives of the function. Okay, this is similar to the integral of f prime x dx equals f x evaluated at the point. Okay, it's very similar, but this is just a surface integral. So it cannot be arbitrary function in the surface integral. It must be the partial derivative of the f. Okay, so which is Stokes find out this should be the curl of the vector field. Okay, yeah, then you can simplify the integral. Just it's very similar. Just trying to do comparison. Okay, now I want to look at the special case. The special case is going to be, let's recall the formula. So if capital F is going to be, if capital F is given by its three components, P, Q, R, okay? I'm not going to mention the variables X, Y, Z here, just for simplicity. Then what is the curl of the vector field? Okay, the curl of the vector field. This is a given in the previous section. It's hard to memorize it, okay? But the formula will be easier to memorize. Just use a matrix as definition. Okay, so yeah, here it is. All right, so this is going to be the three parts here. The first part y minus qzi plus pz minus rxj and qx minus pyk. Right? But if you really forget these details, you should know the formula how to find the determinant, right? ijk. So this will be partial derivative with respect to x, partial derivative with respect to z, and pqr. Okay, it takes about 20 seconds. You can write down the above formula. Okay, so ds is just as a normal vector times the surface element. Okay, then using that you can find you can convert. You have three functions and the three variables. Okay, and then Stokes generalize this fundamental theorem calculus to the surface integral. So if those three components, this is this is a very interesting formula. If the function here, the vector field, right, and is given by this formula, then you can change the surface integral to a line integral. Okay. Now the special case. Let's look at the special case. Actually, the special case is a Green theorem. Special case. Okay. Special case is I only consider the surface, which is just as a domain. So I just only consider the surface. This is the domain D is itself is just a surface. Okay. And in the XY plane. And this is a domain in the XY plane, and this is my surface. It's a flat surface, right? Okay. So F is just equal to P and Q. Now this can be extended to a vector field in three-dimensional space. Okay. So here, more precisely, I have XY, right? PXY, QXY. But this can be extended to XYZ and still PXY because it depends only on XY, right? And QI is 0. So it becomes a vector field in three-dimensional space. Okay. So so what is the curl of this vector field in three-dimensional space? It is based on the above computation. I is going to be 0, Q independent of Z. All the terms P independent of Z, I 0. So only QX minus PY. Okay. So only two terms left. Okay. And the normal vector is nothing but the K. Okay, because this is a normal vector. It's a flat surface. Okay. And the C is the boundary of the domain. It's oriented in that direction. Okay. the Stokes theorem says that this surface integral, because it's a flat surface, so my ds is just dA. Okay, no question about that. So it's a flat surface. So here's S. Okay. Let's write down what is that. This is surface integral, right, over the surface. Okay, and this will be the normal vector ds, right? Since the normal vector is just k, the curl of the vector field is just this above. So it is going to be nothing but the double integral d qx minus py dA, okay? Yeah. You see, the dot product of these two terms is just q sub x minus p sub y. And ds is just dA, okay? Then according to Stokes theorem, and this is going to be the boundary, okay? The boundary is a C, okay? And here this is supposed to be F TDS, right? And this is a, all right, so this F, that is in the plane, right? In the XY plane. This is D, this is C, right? So this inner product is just like a usual line integral. Okay, it is going to be just two components because third component does not play any important role here. Okay, so it's just a P and the Q and dot the inner product. Okay, so this is just the line curve for the vector field in the. You can put the three components here at the very beginning, yeah. And this is going to be 0. And here, the tangent vector has maybe can have three components, two components. Depends how do you view it. It's viewed in three-dimensional space. It's three components, but the first two components will be non-zero. The third component is 0. So actually, this is just the dot product of these two-dimensional vectors. And this is just like a usual line integral of the vector field. Okay. This is on R2. All right, so that's the special case of the Stokes theorem, okay, which is just Green theorem. So Stokes generalizes the Green theorem. Okay. Now how do we use this theorem to solve some problems? Use Stokes theorem to verify. Yeah, that's the first problem we're going to discuss is fxyz, right, equals x squared sine zi plus yj plus xyk, right? And S is the part of the paraboloid, and z equals 1 minus x squared minus y squared, right? That lies above the xy plane, oriented upward. Okay. So what does that mean? Yeah, you need to give orientation for the surface. It's a normal vector. How do you choose a normal vector? Because there are two options, right? So let's sketch the surface. It's hard to draw it, right? Z equals 1 minus x squared minus y squared. So when x, y both are 0, that's z is 1. So I think it's open downwards, this piece. Okay? When z equals 0, you get a circle in the xy plane. A circle in the xy plane. All right? So this surface is oriented upward, means the vector field, the normal vector field is shooting in this direction. It's a normal vector field. So we want to evaluate this surface integral of the curl of the vector field. Okay, so how do you do that? Directly. First of all, you have to compute the curl of the vector field, okay? Which is kind of like a derivatives, partial derivative of f. Then you have to find the normal vector field. Then you find the product, inner product, right? Then you still have to find the Jacobian, like, you know, or what's it called, the area element. Then you have the double integral, okay? It's another double integral over the d, okay? So d is going to be xy, x squared plus y squared less than 1, okay? So it's, you have to parameterize this surface, right? It's complicated, okay? If by the Stokes theorem, just like, you know, in certain cases we use Green's theorem, right? The Green's theorem is used in the opposite direction. You give a line integral, and you evaluate it using double integral. Okay. Now here we have double integral, kind of double integral. We want to evaluate this double integral, but we can change it to the line integral. Okay, it's like a fundamental theorem of calculus in a from high dimension case. Yeah. So according to the Stokes theorem, it's going to be, this is C, the boundary is C. It's oriented in that direction. Okay. So C, yeah, C is the boundary of a D, the domain D. Or domain, it's the same. You have a D is in the XY plane. The surface, this also viewed like a surface, the boundary of the surface. This is noting partial D means the boundary of D. Right? So this is an FTDS. Okay. So now it's easy to evaluate this integral. Okay, it's line integral. If you parameterize this circle around the D, right? And then I is going to be, yeah, in order to evaluate this, I need to parameterize it, right? It's going to be cosine theta, sine theta, okay? Let's say in dimension 2, right? So now what? So this integral is going to be CF dr, right? If we have a parameterization. Then if you use a theta, and that is going to be from theta from 0 to 2 pi, and F, right? And times R prime theta d theta, right? So this is dr. It's also dr, which is also T ds, okay? But S is arc length, but we change it to the theta. Okay, so now let's calculate this. Okay, let's calculate this. So R prime theta is just equal to negative sine theta, cosine theta, okay? If the third component is 0, we are line in 2 dimensions. Okay. The vector field Yeah, we're in three-dimensional case. We better to put the third component, but most time we don't do that. Okay, let me, yeah, we because it's a surface, okay? So we are three-dimensional. So the third component is just 0, but let's use this notation. It's better because vector field F itself, it's not necessarily a vector field in the plane. Okay, F R theta. Let's evaluate. In that case, X is going to be cosine theta, Y is going to be sine theta, Z is going to be 0. So I look at that, it's going to be cosine square theta and sine 0 I. Just plug X, Y, Z into the formula, and here's Y here, sine square theta J plus X times Y, cosine theta, sine theta K. Okay, so along the circle, the vector field is given by this formula. So you have two components. Okay, the first component is 0. Then you look at the inner product. Then F R theta times R prime theta is just equal to sine square theta cosine theta. That's it. Okay. So now this line integral becomes an integral from 0 to 2 pi sine square theta cosine theta d theta. And from here you can just use substitution. Okay. Use substitution, u equals sine theta, right? And du equals cosine theta d theta. Okay, when theta equals 0, u is 0. When theta equals 2 pi, u is 0. It's u squared du, which is 0. Okay. It's 0. Okay, let's review the problem. If you integrate the curl of the vector field over the surface, then you can translate the surface integral to a line integral along the boundary of the surface, which is a curve. Then you parameterize the curve and evaluate the line integral, and which usually is be easier. Surface integral is complicated, as you can see that when you do exercise. You have to find the ds. You have to find the cross product, right? Yeah, you have to find the cross product of the, you have to find the parameterization for the surface first. Then the cross product of R sub U, R sub V, right? So it's not a trivial. It's not simple, yeah. So let's look at the next problem. Now, if we ask you to verify the Stokes theorem, then you have to evaluate the surface integral. You have to evaluate the line integral. If you're assuming, if you are suggested to use the Stokes theorem to evaluate the surface integral of a curl of the vector field, then you just apply that Stokes theorem and change it to the line integral. But if you have to verify the Stokes theorem using the example, then you have to evaluate surface integral and the line integral, and you want to make sure they match. Sometimes it's harder to follow somebody's proof, like the Stokes publishes a paper, and here it says he stated the theorem, but there are several pages. Sometimes use the theorem, you're not use some ideas you're not familiar. It's harder to understand. But then, if you are the referee of the paper, right, what you should do, you just pick up a special example to check if it does not work. Then that's wrong. You don't need to waste lots of time to find out where's the gap of the proof. Okay, that's what we do. All right. So let's look at the following. Let's look at the following vector field: yz, I, yj, 3xk. S is a part of the paraboloid of z equals 5 minus x squared minus y squared. What I'm going to do is to evaluate this surface integral. Okay. Also evaluate this double integral, this line integral. Okay. C is going to be f t ds. Okay, which is also equal to c f dr. Okay, if parameterization is given. Okay. In the book, they're not going to write this form. Okay, that's the definition. This is the same here. It's going to be curl of f, the normal vector ds. Okay. Oops. Okay. So yeah, let's do one by one. Okay. I want to, yeah, if we are asked to find the evaluate this surface integral. Now what I have to do, that's a good example, right? So you draw the picture first. This is surface opens downwards. Okay, it's a 5. And the plane is xy. This is here's a z equals 1. Right? And this is a surface, and C is the boundary. Right? Oriented upward. That means you are given the normal vector point outside. All right. So what I'm going to do, I needed to find the curl of the vector field. I'm not going to use the Stokes theorem to change the the surface integral to a line integral. Okay. So it's a little bit complicated, but we have to do that. We should have enough time. I hope I have enough time to complete. So let's go back to look at. If we forgot the formula for the curve of the vector field, I suggest you always use this. Okay. And where's my vector field, right? It's going to be negative 2yz and the y and the 3x. Okay. Let's find out. So you open this part for the I, okay? And it's clearly it's going to be 0. 0 minus 0, I, minus, and then you look at, delete the second column, first row, right? So I got 3. When I differentiate with respect to z, minus, it's plus 2y. Okay? J. Okay. Minus 0 minus is plus 2z. Okay. Okay. So that's the vector field. Okay. That is vector field. So it's going to be negative 3 plus 2y and 2z. The first component is 0. Okay. You can write it in this form. Now the difficult part is still have to find the normal vector field. Okay. You know that 5 minus x squared minus y squared equals 1, right? That gives you the equation x squared plus y squared equals 4, which is 2 squared. It has a radius 2. Okay. So that's the intersection part. Okay. This is a curve C. Okay. And so you can parameterize the surface by the following x, y, z, and 5 minus x squared minus y squared. But here x squared plus y squared is on the D. It's less than or equal to 4. Yeah. How do you view it? Yeah, look at the picture again. This is in the xy plane. For that piece, this is a domain D here, right? The domain D, the circle is x squared plus y squared equals 4. You can determine that, right? Because coming from this, its intersection was a plane, z equals 1, okay? All right, so let's calculate the normal vector field. It's complicated, right? So Rx, if you already know the formula, yeah, the cross product, I skipped maybe some steps, negative of the partial derivative of the first function, right? Remember this, right? Yeah, remember that. So here, f, this is my f. Right. So I got 2x, 2y, and 1. Okay. So the surface integral, it's not too bad. The surface integral of the curve of the vector field and ds is going to be the double integral, the curve of the vector field, and here's Rx plus Ry and dA. Okay. Let's look at the cross product. Where's the curve of the vector field? Curve of the vector field is the first component is 0. Only the okay, so this is going to be let me write down the first component 0. Second component is negative 3 plus 2y. The third component is 2z. Okay, it's harder to memorize. And this will be 2x, 2y, 1, and dA. Okay, not too bad. The product is going to be negative 2y, 3 plus 2y, and plus 2z, and dA. Okay. So we simplified 6y plus minus 4y squared plus 2z dA. Now, be careful. Yeah. All right. This is a double integral, right? Where's my z here? I think I have to put the replace z by the f, because z equals f. Okay. So for the on the surface, yeah, on the surface, the curl of the vector field at every point is given by the above formula. But the z is going to be 5 minus, yeah, z is actually on the surface, z is going to be 5 minus x squared minus y squared. So that's why I have to put it here. But 2 times 5 minus x squared minus y squared dx. Okay. So finally, I got 10 minus 2x squared minus 6y minus 6y squared, because negative 4y squared minus 2y squared is 6 squared. Right? So this is a double integral. Oh, I ran out of time. All right, so this is how do you directly to evaluate this integral, surface integral of the curved vector field. Okay. Then the d is going to be, remember, is going to be the disk. Okay, x squared plus y squared equals 4. D is less than equal 4, right? So you can use polar coordinates to evaluate this double integral. Okay, so if there's one step away from making computation mistakes, the rest of them, you will not get the right answer. But I will check the details, if just only one small mistake somewhere, if you can complete all the procedure, then you only lose 20% of credits, okay? So, but if you get very strange functions, maybe something's wrong. So the line integral, this double integral now, become iterative integrals from 0 to 2, 10 minus 2, 2 times cosine theta squared minus 6 to sine theta minus 6 to sine theta squared. Okay, and remember this is supposed to be R, right? R and the D, R d theta. Hold on. So this is not just 2. This is 2 in the place of 2. There's R here. Okay, it's not on the boundary. It's inside. R is between 0 and 2. Okay, X, the spherical coordinate, a polar coordinate, X equals R cosine theta, Y equals R sine theta. So you plug into the formula, and then you evaluate this integral. Okay. It's not a trivial. Okay. So yeah, let me write down the details here. So R multiplies 10 times R, and here I have a 2R cubed cosine square theta, and here negative 6R square sine theta minus 6R cubed sine square theta d theta. Okay. So if you evaluate the integral with respect to R and theta, okay, so you can, yeah. So this is the entire derivative 10I is going to be 5R squared, right? So you will get 5 times 2 squared minus the entire derivative R cubed is going to be 2 over 4 R to the 4th power. So when you simplify this, okay, and the entire derivative of this will be 6 over 3R cubed. So it'll be 2 and 2 cubed sine theta, and minus 6 over 4 R to the 4th power. it will be 3 over 2 and 2 to the 4th power sine square theta d theta. When you look at this, you find out that the integral of sine theta is going to be 0. Okay, cosine theta. Yeah, let me simplify. Right, so cosine square theta is going to be half of 1 plus cosine 2 theta. Then you can ignore the cosine 2 theta because the integral cosine 2 theta from 0 to 2 pi is going to be 0. So my answer here will be, this is a 20 times 2 pi minus 2 pi minus, minus, this is going to be half of 1 minus cosine 2 theta. So it's 1/2. So it's 24. So be 24 times pi. Okay. So 40, yeah. So finally, I'm running out of time. Finally, so 40 minus 26 will be 16 pi. 14 pi. All right, so this is a surface integral of the vector field. I don't have a time to evaluate the line integral, but then they should match. So they should match, but the line integral will be much easier to evaluate. Okay, let's take the quiz, and I hope I can complete the lecture notes when I get to my office.